Good evening, ladies and gentlemen. Welcome to this new video. In this video, we're going to be looking at our ESSRT page number 11, the bottom part. The last time we looked at the upper part of that page 11, and we looked at the various internal layers of the earth. This bottom part talks about the earth crust and how the earth crust is broken into pieces. So a lot of information that we can extract from this. Is so much going on here that meet the eye. So what we're gonna do is we're gonna try to scratch the surface a little bit and break down each of this piece of this diagram into piece by piece, and then we're gonna bring them all up together, and hopefully it makes sense. I feel strongly if we use a colored version of this reference table page, it will be much more easier to understand and comprehend what is going on in this reference table page 11. So the upper part of this diagram, I'm going to slide it right across here. Okay, so the upper part is the black and white, the one you have on your reference table sheet, and then the one at the bottom is more colorful version of it, and with more details that are not represented in the black and white version that you have in your reference table. So if you need to pause the video and do some comparison here and look at some of the details that are provided in the colored version that are not represented or that are not given to you in the black and white, and you can quickly replicate those information into the black and white version that you have. All right, so this is the version that we're going to be working with for the next couple of minutes, and then we'll extract everything that we've learned, and then we're going to put them on the black and white version that you have. For us to really break this down and make sense of it, we're going to look at a quick review of what plate boundaries really are. Now, the earth crust, both the oceanic and continental crust, is resting on a liquid layer called the asthenosphere that we looked at last week. Now, as a result of this, the earth crust is broken into pieces, right? And each of these pieces are referred to plate. Each of these pieces are referred to as plates. So between one plate and another plate, you have to score the plate boundary. So this plate boundary behaves in different ways, and we can group them into three categories. First, we have the divergent plate boundary. All right, so diverge from the word divide, from the word divorce, or to separate. So divergence simply means the plates are separating. The boundary between the two plates is spreading, which means the two plates are moving away, drifting away from one another. And then you can see that arrow right there representing that relative motion. And as these plates separate from one another, the lava or the magma from the asthenosphere has wiggle room to come to the surface, to spew out to the surface as that process goes on, as that diversion or separation takes place between those two plates. The other kind of plate boundary that we have is the convergence, to come together, create a confluence, communicate, converge, to meet. All right, so in this situation here, we have two plates colliding, going head to head with one another. And when that happens, one of the plates usually would go under. The one going under is subducting. All right, think about it like a submarine. So it's subducting, going downward. All right, so that word right there, subduct, to go under. So now this happens when the two plates are meeting and one of them is going under. The one going under goes deeper into the earth, and as we learned, the deeper you go into the earth, the hotter it gets. So as a result of that hot temperature, the subducting plate begins to melt, and as that melting takes place, it pops back up. Remember what we said about hot lava or hot gases or hot liquid? hot liquid rises while cold liquid or cold gases sink. All right, so once this part of the earth crust subducts, it is melted, and then as a result of that melting, it goes back up and creates a volcanic eruption there, creating a volcanic mountain right around that area. So that's what happens in the subduction in the convergent plate boundary. The last kind of boundary is the transform plate boundary. The transform plate boundary, the plates are simply sliding by one another. All right, they are sliding by one another in that manner. So the plates are neither coming together nor separating, but they are just sliding by. So we call it transform plate boundary. Now, those are the three kinds of plate boundary. So we're going to bring all of those information into this page that we are looking at. First, let's start here. We know that the convection current creates that convection movement that we talked about in class. So as the hot lava rises, the cold one sinks. So as that process continues, it cracks up this part of the earth right here. So which means this part of the earth is going this way and this part is going that other way. So this therefore is a divergent plate boundary. It's a divergent plate boundary. So because the plates are separating, lava would rise up, all right, and pop up to the Earth's surface just below the ocean. Now, creating some little mountains, some underground mountains. So these mountains are created, but they are underwater. So these underwater mountains are referred to as ridges. All right, they are referred to as a ridge or ridges. Sometimes you hear the word mid-Atlantic ridge or mid-oceanic ridge because they usually occur in the middle of the ocean. So the word mid means middle, and then ocean ridge. So you know what a ridge is. A ridge is the underground mountain that is created by lava rising through the separation of two plates. All right, so that's how ridges are created. Now, when it is two continental plates separating two continents, we call that a rift. All right, we call that a rift. So a ridge and a rift are formed when two plates are separating. All right, cool. Now, next, let's talk about when the plate converges. So here we see this plate is coming this way, and then we see another plate coming this way. So they are going head to head, and then one of them subducted. Now, you will notice that it is the oceanic, the one below the ocean, that is subducting. This is because the oceanic plate is more dense. The oceanic crust has a density of 3.0 grams per cm cube. Why this continental crust, if you watch here, this is the continental crust. So this continental crust has a density of 2.7 grams per cm cube. So if you are denser, it means you are heavier. So you should be the one going under. So we see that the oceanic crust is the one going under here. And as that subduction continues, as that diving continues, it is heated and melted, and that melting causes lava to rises up, causes the hot lava to rises up, thereby creating volcanoes here, and volcanic mountains. So you see that all of these mountains are occurring in sequence at the same time. They are, simply put, these mountains are giving birth to like triplets or quadruplets, as the case may be. So these mountains come from the same process. All right, so all of this is referred to as subduction volcano because they are all volcanic mountains created by the subduction of one plate going under. All right. Also notice that when two plates meet, as one of them goes under, it creates a depression. As one of them goes under, it creates that little depression right here. Okay, so that depression is called a trench. All right, so this is ocean ridge conversion margin. We can call all of that trench. All right, something we're going to annotate pretty soon. You're going to see that in your reference table as well. So that is what happens in a convergent plate boundary. Next, we're going to talk about hotspots. Hotspot is a place where the plates are neither meeting, the plates are neither diverging or transforming, but rather a part of the crust itself is so thin that it allows volcano to just pop up on its own right in the middle of the plate. Now, that place is called a hotspot. Simply means it's a part on the crust that is so hot it allows lava to pop up. Now, when the lava pops up, it creates a volcano. And when those volcanoes are able to stick their head up above water, they create a land surrounded by water. So we call that an island. All right, an island is a piece of land surrounded by water. Now observe that this plate is moving rightward. So you see that previously, these other three volcanoes used to be directly on top here. In other words, the current volcanic eruption taking place now is the recent one. This 1, 2, 3 as the one that have occurred before, which means the one I just labeled 3 used to be directly on top the hotspot and created that volcano. Then as the plate begins to move further to the right, 2 was created. As it moves further to the right, 1 was created. And then as it moves further to the right, this new one, I'll call that 0 now, is being created. So you get that sequence. So that is how many of the islands around the world were created. A typical example is the Hawaii island that we have in the United States. This is how that island was created, or those pieces of islands were created. Lastly, we're going to look at what happens in a transform plate boundary. Transform plate boundary is when the two plates are just going by, transforming by one another. So that happens here. This is going this way and this is going the opposite way. So in between the two, we have that crack. That huge crack right there is what we call the fault. So it's called a transform fault because it is the fault line. It is the line of weakness. It is the crack that exists between the two plates that are sliding by, transforming by one another. Hence the word transform fault. All right, so pretty much that is a wrap. I think we can go deeper than this, but I think we shouldn't make this longer than necessary, but we're going to get deeper and deeper into it. And that brings us to our black and white reference table, page number 11. If you've been following, you should have annotated all of this information that we've learned already. So let's start. First, we have the situation where the plates are diverging. So this is diverging because the hot magma is rising and popping up, right? That is because hot lava is rising up and going this way, and then the cool one is going down and going that way and going down. We saw that in the colored version. So the lava is going up this way because it's hot, and then the cool ones are going downward because they are cool, and we said cool lava would sink. Hence, lava has a chance to spill out here. As a result of that spilling, a ridge is created. An oceanic ridge is created. And then we said a ridge is an underground mountain. That is a very important annotation you should put in your reference table. A ridge is an underwater mountain. Okay, now take note that this is an ocean, so you have to follow that line and imagine that ocean in there as you saw that in the colored version, right? And then this is the continent, of course. So this is the continent, and then we have the depression carrying the ocean right there. So all of these crust below the ocean are the oceanic crust, and all of this crust below the continent are the continental crust. Okay, let's move forward. In the case of a conversion plate boundary, we see that the two plates are meeting and one of them is subducting and going under, while this is going the opposite way. So the two plates are converging and one of them is subducting. And of course, it is the oceanic crust that is subducting because it is more dense with a density of 3.0 grams per cm cube, while the continental crust is riding over. So as the oceanic crust subducts, it is melted and heated, because the deeper you go into the earth, the hotter it becomes. So as a result of that heating and melting, the hot lava becomes less dense and it pops back up, and it goes back up as a volcano, creating a chain of volcanic mountains, and then we call that subduction volcano, or those group of mountains are the edge of the continent. Then we said when these two plates met, as they were going down, as one of them was going down, it creates a huge depression right here, and that depression we're going to call the trench. So the trench happens when two plates are meeting and one of them is subducting, creating that little depression, right? I mean, I shouldn't use the word little. Trenches are the deepest parts of the earth. So it's not, I take back the word little. All right, next, at the transfer plate boundary. At the transfer plate boundary, we have the fault, all right, because for two plates to successfully transform, slide by one another, there have to be a fault line, there have to be a weakness in there. So that gap or that fault, that crack, is what we refer to as fault, right there. Okay, pretty much I'm gonna just put some more arrows in here. Remember, this arrow is conversion, and remember, this is the hot spot. The lava is going up and popping out that volcanic island there, and if that volcanic mountain stick its head above water, we have an island, and that these highlands are moving in that direction. Therefore, this island labeled A is older than B, and B is older than C, and C is older than D. So it's increasing in age in that direction. So do take note of that. Um, Pretty much that would be a wrap. Next, I want to just quickly highlight what they mean by tectonic plate. One here, so that is one plate, one crack of the earth. So the earth crust is broken down into several pieces. So one piece is a plate. So tectonic plate 1, we have tectonic plate 2 here, we have tectonic plate 3 here. Tectonic plate 3 is the continental crust, tectonic plate 2 is the oceanic crust right here, and then tectonic plate 1 is the other oceanic crust that is sliding in that manner, transforming in that direction, while this other one is transforming in that direction. So do take note of that. Okay, with this few knowledge, we're going to quickly answer some questions, and we call it a wrap. Question number 1. Which cross-section diagram of a portion of the earth crust and mantle best shows the pattern of the mantle convection current that are believed to cause the formation of mid-ocean ridge? Convection current, that's an important phrase right there. And then ocean ridge, we just talked about that. Now, ridges are formed when the plates are diverging. So it has to be a divergent plate boundary. So the plate must be separating. All right. And as a result of that separation, the lava must be able to rise up. Okay. So if that is true, the heat must be coming from in between at the center there, right below the ridge itself. If that is true, then this arrow should be moving this way, and this arrow should be moving this way. A cannot be our answer. C cannot be our answer either. It has to be right, hot lava rising and cold one sinking. And you remember that hand gesture. It has to be that hand gesture. So C and B is out of the way. T looks like our right answer, with the lava rising up right there, and with the heat coming in right there. And then we have the arrow going that way, and then the arrow going that way, and then the cool one sinking. And then we have a convection cell right there. D is a correct answer right there. Question number 2. The accompanying diagram shows a cross-section of a portion of the earth. The inferred motions of crustal plates are shown. Letters A through D represents location on Earth's surface. Which letter represents the location of mid-Atlantic ridge? All right, mid-Atlantic ridge, that's a new fancy word, but at least we know what that word ridge means. Ridge is an underwater mountain, so it has to be somewhere around. That's why it used the word Atlantic, because the Atlantic is an ocean. Okay, All right, so if it's mid-Atlantic Ocean ridge, then it should be under the ocean, and it should be somewhere where the plates are separating, because ridges are formed in a divergent plate boundary. In a divergent plate boundary, the plates have to separate to create that rising lava that would create the underground or underwater mountain. So if that is true, option A cannot be our answer, because option A, we see this arrow coming this way, we see this arrow coming this way. So this is a convergence. So A is actually technically a trench. So A is not our option. B is a mountain, it's a volcano. B itself is the volcano that pops back up. If you look at your reference table, whenever you have a convergent plate boundary and one of them is subducting, it pops back up to create mountains. So that's what B is. C, divergent, definitely. C looks like our answer. D, on the other hand, represents what now? I'm not sure. That's that an ocean? Land? I don't know, but definitely it's not our answer. C, it is. Question number 3. Which feature is commonly formed at a plate boundary where oceanic crust converges with a continental crust? So there's a convergence, which means the two plates are going head to head. So if it's conversion, what is created? A ridge is created when it is divergent. So A is definitely not it. An ocean trench? Yes, a trench usually occurs when two plates meet. So that sounds like it. Our answer should be B. Let's see. Transform fault. A fault happens when the plates are just passing by one another. So C is not our option either. New oceanic crust? No. Our answer is B. Question number 4. What are the most likely geologic ages of the volcanoes B and D? So let's look at this diagram here. The diagram shows a hotspot here. So the hotspot is popping out volcano in that manner. So A is the current volcano taking place right now, and then the plate is moving in that manner. So if the plate is moving rightward, that means D must have been created first, then C created second, B created third, and A is currently being formed, created fourth, so to say. So if C is 8 million years, D must be higher than 8 million because D is older. And B should be younger than 8 million because B is younger than C. So B is 5 million, younger than 8 million. Okay. D is 12 million, bigger than 8 million. Our answer sounds like A. But let's see. B is 2 million years old. Younger, yeah. Why D is 6 million? No, D cannot be younger than 8 million. So that is out. B is 9 million, which means B is older than C. No, C is older. C was created first before B. Yeah, C is out. B is 10 million. No, B has to be younger. B has to be younger. This must be younger, and this must be older than 8 million. All right, last question. Which block diagram best represents the relative direction of plate motion at the San Andreas Fault? San Andreas Fault is a place in California, something we're going to look at later on. But I see the word fault, and I know fault does have to do with transform plate boundary when the plates are just passing by one another. Option A doesn't look like it for me because one plate is going this way while the other is trying to go the other way. So that does not look like a transform to me. Option B is a divergence. The plates are separating in opposite direction. That's a divergent plate boundary. Divergent plate boundary creates ridge and ridge, so it doesn't create faults. Option C, the two plates are coming together, converging, and when they converges, a trench is formed, and then volcano pops out, right? A subduction is also formed, so that has nothing to do with fault. C definitely is not it either. Option D, the plates are just sliding by one another, so the crack between the two of them is what I'm going to call fault. So our answer therefore should be D. Gentlemen, ladies, that's a wrap for this video. See you all on the outside. Take care.